There you go. Go ahead.
Okay. One of the thoughts is this is designed to be a short talk. And maybe after the talk, what we could do is we could do a tour of the observatories. Would anybody be interested in that? Going around to the observatories, let me show you what's inside. All right. Well, let me start with this talk first. I was working late last week on a proposal. And the proposal was something that was supposed to be launched into space. And I was thinking about all the different steps that are involved in putting something into orbit, and I thought it'd make a really cool talk. So this is sort of what it is. I'm not covering everything, and I'm really glossing over a lot of stuff. But this is basically what you need to know if you want to launch something into space. Button, arrow key. Okay, how do you advance the slide? How about that way? Yes. Okay. The first thing you got to worry about is how are you going to get it up there? The way it used to work is you had to order the launch system at the same time as you ordered the satellite, because the lead time on the launch system was as bad or worse than actually building the satellite. Now, this is back in the days when pretty much all rockets were custom jobs. And it turns out that up until about 2010, they all pretty much were. If you got something small is actually pretty easy. And a lot of the times with something small, we would use something called a getaway special. You would get a satellite that was being launched that had extra room, extra payload. Because for some rockets, you've got a maximum size and a minimum size that you can put in the rocket. So a getaway special is great. It's just a little thing that's attached under the satellite or beside the satellite. We had one case many years ago where they actually launched 50 pounds of sand in sandbags. And the reason why they launched it was because the satellite was actually underweight for the launch vehicle. And it wasn't quite symmetrical, so they put 50 pounds of sand on one side to balance it. Now, it turns out that there are actually some really good plans for launching small satellites. You've got the Firefly, which you can basically think of as a mini SpaceX. It's reusable. You've got the Rocket Lab, which is, they're hoping to make it reusable. Right now, it's expendable only. And you've got the Pegasus. And the Pegasus is actually launched under the wing of a 747. And it's actually a jet that goes off into space. Medium-sized satellites. You got the Ariane 6, we can do up to 10,000 kilograms. The Soyuz at 8,000 kilograms, and they're both doing commercially now. And of course, the Falcon 9. Now look at how big the Falcon 9 is. Basically double what a Soyuz can take and put into space. And that is a totally reusable rocket. Now, if you compare the Falcon 9 price, the Falcon 9 price is roughly 1/10 of the price that we used to pay to launch something into space. And with Super Heavy, which is what they're planning on doing next, it's going to be even less. So it's a major, major advance in getting things into space. And the satellite, which is off to the right, is a satellite called Iconos. And Iconos is very special to me because it was the first satellite that I ever worked on. Yes?
Me too.
You too? Great. Iconos is actually developed at Kodak. And I was working at Kodak at the time. And I actually worked on several of the chips that are in the image processing block. What'd you work on?
I was doing PCB design.
You did board design. Okay, yeah.
Did the flat surface.
Yep. But it was a cool design. And we're actually still designing stuff off of that initial base now, although time has really marched by. If any of you has used Google Earth, the initial version of Google Earth came from that satellite. All right. What if it's really big? You've got the Atlas V and the Vulcan and the Falcon Heavy. Now, the Atlas V is being end-of-lifed. The Vulcan rockets are still being used, but they're actually being used now with Blue Origin engines. The Vulcans used to be launched for about 10 years. They were launched with Russian engines, and they ran out of parts for the Russian engines. They still have the engines. The problem is that the fuel tanks for those engines are built in the Ukraine, and the Ukraine is currently at war. Therefore, they switched all their production over to war production. You can't do that anymore. Jeff Bezos is working on a competitor for the Falcon, which is called Blue Origin. And he's already developed his engines, although he doesn't have the software working yet, for his Blue Origin rockets. So what they're doing is they're using them in the Vulcans now. There was a rocket called the Delta Super Heavy. And for 50 years, that was the workhorse for getting something really big up into space. The last one was launched this year, and there will never be another one made. It turns out that they were all custom jobs, and they all, like I said, had to be pre-ordered. When you were building your satellite, you had to pre-order the rocket to launch it into space. Lockheed never built a standardized production line for that rocket. So they were all one-offs. All right. What else? Sometimes it's a rough ride. Pyros, explosive bolts. The one thing that we really had to worry about on Iconos was it turns out that our box was sitting right next to the explosive bolt that released it from the second stage. So basically we had a bang that went right through our circuit boards. Shake and bake. Every single system has to go through shake and bake. And what they do is they shake it really hard to simulate a rocket taking off, and then they cook it to 200 degrees, and then they drop it to minus 55. And they make sure that it can survive and all that. When they took the James Webb Space Telescope and they put it through shake and bake, they found 2 nuts and a bolt sitting on the floor under it. So they had to take the whole thing apart and put it back together again and fix the loose bolts.
Doing better than Boeing.
Yeah, that's actually another very sore subject. The Boeing Starliner was on a 10-day cruise to the International Space Station. They've been up there for 50 days now, and they're not letting them come back down until they figure out what the heck's wrong with the Starliner. So these guys are getting an extended stay in the man and woman are getting an extended stay in the International Space Station. All right. Temperature extremes. On the sunward side, you're in the 200 degrees. You're in 200 degrees. On the night side, you're down to minus 55. It gets hot and it gets cold. Also, you got space junk. And this is a simulation of the junk that's in Earth orbit. It's all over the place. It's proliferating. Things are whacking into each other and causing more pieces. Some guy back in the 1960s thought it'd be a really cool idea to send some chaff up into orbit. Basically little strips of aluminum. And they're still floating around up there. The International Space Station has now been hit twice. Fortunately, nothing ever hit any of the main body. Yes?
It's something you mentioned, the bag of set. what happened to the compared to the space?
What happened to the what?
You mentioned the bag will be sent to develop the weight.
Yes.
So that has to be spread.
Yeah, the weight has to be symmetrical on the spacecraft.
That sand will be space.
Sand will be space junk.
Yes. We have to set up everything now that we send up has to have a deorbit policy. So if you send it up, you got to have a way to bring it back down again. If you're sending it up into geosynchronous orbit, then the deorbit policy is usually to send it up into a higher or lower orbit and shut off its transmitter. One of the big problems that we have is that the Russians decided to use this really cool gamma ray source as the power for some of their satellites. And these things are screaming in gamma radiation up in geosynchronous orbit, which is causing all kinds of problems with things that are sensitive to gamma rays. Yes?
Will all junk eventually fall back to Earth with Earth's gravity pulling it?
Eventually. There are things up there that are in what are called forever orbits. And the orbit they calculate will last for a couple of million years. And that's until something comes by it and perturbs it. Also, things keep on coming back into the system. About 10 years ago, the limb from Apollo 10 wandered back into the solar system and then wandered back out again. And that limb has RTGs on it, radioactive radiothermal generators. So we could tell it was coming through. Now, another weird effect you have in space is something called vacuum welding. If you take two pieces of metal and you just sit them on top of each other, after about 2 years, they weld themselves together. And it's not like on Earth where you can take a 10-year-old boat, you just put a little elbow grease into it, take it off. The atmosphere actually acts as a lubricant. In space, you don't have that. And the metal simply migrates into each other. And sometimes the only way you can get it apart is by either sawing it apart or using explosive bolts. How are you going to power the thing? Pretty much everything we do these days is solar powered. Some things are radiothermal generators. Radiothermal generators are really cool. They're made from little balls of plutonium. There's an example of one on the right. And what they are is they're little heat sources. And they can use the heat to actually create electricity to power the device. The Voyagers are powered by RTGs. The rovers, the Perseverance rover and the, what's the other one? Come on, Dave. The two rovers that are on Mars right now are both powered by RTGs. The RTGs were for, up until the 1960s, manufactured in North Carolina. And in North Carolina, in the 1960s, they manufactured the last of this plutonium. So how are we getting these things, you ask? It turns out that in Russia, there is a town that is powered solely by a radioactive generator that is producing plutonium. There used to be 3 of them. Now they've taken it down to 1. But Russia is still producing this stuff. And that's how we're actually powering our probes that need RTGs, is from this plant in Russia. And the only income that plant has, other than producing electricity, is selling these radiothermal generators. So even though Russia is technically at war, they're still selling it to us.
Is that plutonium?
Plutonium, yes.
Heard about thorium.
A thorium reactor is actually better than a uranium reactor. Thorium is much more abundant, it's all over the place, and it works just as well in a pile as uranium does. There's only one problem. You can't build a nuclear bomb out of it. Therefore, this fellow by the name of Rick Tobin who was the guy who was the father of the atomic fleet, for bad, it's research. Because you can't make bombs out of it. Therefore, it's totally useless, right? Now, there are people who have actually looked into actually building thorium reactors for cars. Because the stuff is actually relatively safe. Like I said, you can't build a bomb out of it. Yes, it is radioactive, but it's radioactive in alpha particles. And alpha particles won't even go through your skin. So it's great, but we're forbidden to work in thorium per the US government. Now, the other thing we sometimes use are fuel cells. Fuel cells are actually really cool. You take oxygen and you take hydrogen, and you have a plutonium plate in the middle, and you just feed both sides. And what happens is that the electrons feed through the plutonium, and when they do, they free an electron into the plutonium plate, therefore causing electricity. And the result is called water. That's the byproduct of it. So these things are actually really useful in manned flight missions. Yes?
You said plutonium plate, you have to have two plates, right, to make a battery?
Platinum. Platinum plates. Platinum plates, sorry. It's only,
Two platinum electrodes or just one?
I believe it's just one. Right now they're actually working with platinum ion, with a platinum ion of some sort. There's actually a Google facility in California now that has 4 giant black boxes that are sitting outside of the facility. And those 4 giant black boxes are nothing but huge fuel cells. And they've got a little hydrogen cap that they cap off of. They pull oxygen out of the air, and that's how they power the facility. So yeah, there are solutions. The problem is that people aren't looking into them enough. Just 2 years ago, there was this major breakthrough they made with batteries. And they've actually achieved the holy grail of batteries, which is a battery basically the size of a refrigerator that you could put in your basement that would have enough power to power your entire house for a year. That'll recharge in 1 day. And it's been developed. But the people who produce power in the United States don't like it, because suddenly you're not on the grid anymore. So guess what they did to the research? Yes.
They bought it and buried it.
They bought it and they buried it. Exactly. So when people,
Chemistry did that better.
I don't off the top of my head, but I do remember the article, and you could probably do a quick Google search for it to find it. Radiation levels. Okay, if you're in low Earth orbit, you still have to worry about radiation, because the atmosphere actually shields us from an awful lot of stuff. You've got CMEs, which are very high energy particles that come through. And they will actually hit stuff, and they will knock electrons off, and they will actually cause errors in your circuits. So what you have to do is, when you make electronics for these things, you have to have redundancies. And for something which is going to be stored for a long time, you have to have a check circuit for it. Because every now and then, we calculate every 100 days, one of these things is going to hit you, and it's going to knock one thing in your computer circuit off. So if you've got a register, that register has to have a checksum in it, so you can fix that error. Okay? In geosynchronous orbit, life is worse. You're further up and above the Van Allen belts. You've also got solar radiation effects, and you've got galactic radiation effects. And yes, these almost light speed fast particles, which are teeny tiny particles, some of them the size of an electron, are coming right through you all the time in space. The effects on imagers are pretty bad. The Hubble Space Telescope has to actually take 2 pictures and then subtract the bad images before they can actually give you an image. Because if they take 1 shot, it's going to be covered with all these CMEs. The South Atlantic anomaly. When I first started doing this, the South Atlantic anomaly was actually over here. Now, it turns out that the Earth has an inner core and an outer core because of the really, really, really bad day when something the size of Mars hit the Earth and formed the moon. So there's 2 cores. There's this inner core, which is the original Earth, and then there's this core of the Mars thing surrounding it. Because of that, and because of the loneliness, you can basically think of the Pacific Ocean as a giant impact crater. On the other side of the Pacific Ocean is the South Atlantic anomaly. The magnetic field of the Earth is actually in about 100 miles over that area. And the problem with that is the Van Allen belts actually come down and they almost touch the surface of the atmosphere. So there's no way whatever you launch up there cannot go through this. So it's going to go through those radiation zones. And what we did with Iconos is we actually turned it off when it went through those zones and turned it back on again after it came out. But the zone, because the Earth's magnetic field is fluctuating and starting to flip, like it does every about 10,000 years, it's moving and getting bigger. And it turns out that parts of South America have already depolarized to north. How to keep it stable? Okay, you've got it up there. Once you've got it up there, it's a smooth ride. And I mean smooth. You can't detect any vibration at all. But you're coasting around up there, and there's a little problem. The Earth's gravity field is not perfectly stable. It's got lumps in it. You hit a lump, you go down a little bit. Hit another stable, you go up a little bit. So what you've got to do is you've got to have thrusters. And the thrusters have to keep you in a nice stable orbit. You also need those thrusters to deorbit the thing at the end of mission. So you've got to leave some juice in them so that you can actually deorbit at the end of mission. You also use gyros. And this is a view of the reaction wheels and gyros inside the Hubble Space Telescope, of which one of them is currently working. The gyros actually keep the thing pointed in the direction that you want. And a gyro is actually a pretty simple thing. It's just a spinning wheel. And if you've ever played with a gyro, like if you play with a fidget spinner, and you move it side to side, you notice there's a little push when you go side to side. The gyros are used inside the thing to keep it stable. They're a very simple device. The problem is they're moving. And moving devices eventually fail. Okay, next problem, how to talk to it. In geosynchronous orbit, when I was a kid, you got a dish for your house if you lived in the middle of the country. And your dish was 6 feet or 12 feet in size. Okay? And it had to be that big because you're talking to something up in geosynchronous orbit, and these things didn't have a lot of power, and they were widely spaced apart by about 5 degrees. So your satellite was pointed up, and you had 5 degrees worth of room that you could get things. Okay, now they're going to 2.5 degrees. And now they're talking about making it even less. And you notice the satellite dishes are now about that big. And the ones SpaceX are using are about that big. okay? And the problem is we're basically running out of room up there. There are so many things up in geosynchronous satellite now. One of the tricks that I like to pull is you take your telescope and you figure out the angle at which the geosynchronous satellites are at, and you just take your telescope and you point it at that angle. And it turns out you can be off by about a degree, and you'll still get them. And you sit there and look through your telescope, and you'll notice that the stars are moving and the satellites are not. And it's a really cool effect because you can actually watch these geosynchronous satellites. Some of them are big enough and bright enough so you can pick them up in your telescope. A lot of the things that they're doing now is they're using different frequencies. So there are different frequencies to talk to different satellites. But like I said, we're running out of that sort of thing. In 2005, one of the satellites that CNN uses actually decided to malfunction. And it started screaming at full power in every frequency that it had. And they couldn't communicate with it, so they couldn't tell it to go into stable orbit. So it very slowly drifted all the way across the United States and out over the Atlantic. When it got out over the Atlantic, it lost power and it contacted Earth. And Earth gave it the command to reset it, and now it's perfectly happy again. I'm still using it. But this thing must have caused everybody heartburn, because every time it would pass in front of their satellites, it would overwhelm its communication back to Earth. So what they did is they went from satellite to satellite. So while the thing was in front of your satellite, you moved all your transmissions to the satellites around it. And then you had people move their dishes. Now, what's happening now is LaserCom. And LaserCom is the latest thing. And here we have an example of LaserCom from the International Space Station. It goes up to a new version of the TDRS satellites, which are the tracking and data relay satellites in geosynchronous orbit. And a laser beam shoots up to that satellite and then back down to Earth. And they read the data via the laser beam. And that's much, much faster than using radio. And of course, you've got the Deep Space Network. The Deep Space Network is a network of telescopes all around the globe. There are 12 of them now, I think, that are communicating with things in deep space, like Mars, Voyager, Bipep Combo, which is going to Mercury, and so on. One of the things they just did with a probe called Psyche is Psyche now has a laser comm on it. So they can use a laser beam to send data back to Earth. And the latest image from the Psyche probe was actually sent back via laser comm. And L3 Harris is very much hoping that they will go for that, because what it means is we get to replace all the relay satellites. Pardon me. And lastly, orbits. You got low Earth orbit, geosynchronous orbit, and Lagrange orbits. The James Webb Space Telescope is in a Lagrange orbit. And Lagrange orbits are stable spots, like way out beyond the moon. There's also a kind of orbit called a Melania orbit, which the Russians use a lot. And the Russians use those to communicate with their cities that are very far north, and the United States uses them too. What they are is they're very elliptical orbits. And they come down to Earth, they go very close to the Earth on the south, but they go very far from the Earth on the north. And because of that, they can use them, you can use them basically as northern geosynchronous satellites. Because once you get above 50 degrees north, you can't point your antenna down far enough to get to the equator. And that is all that I have, folks. This was actually designed. This is actually designed to be a short talk. So how did I do? Not bad, half an hour. All right.